Hello students, last time we have discussed structural theory of organic compounds in part 1. Up to hybridization we have discussed. Now we will be discussing again hybridization but with examples. We will take examples under each hybridization and in detail we will be discussing in this part 2. Now, coming to sp3 hybridization, as I said earlier in the part 1, 1s and 3 p orbitals are combining, forming 4 new orbitals having identical energy, and all the 4 orbitals are occupying the corners of a regular tetrahedron. And hence the hybridization is called as a tetrahedral hybridization and the carbon is known as a tetrahedral carbon. Now, such a carbon where all the 4 bonds are sp3 type, each bond is said to be sp3 type. These sp3 bonds overlap with the s orbital. This is the s orbital of the hydrogen atom. All the 4 sp3 orbitals are combining with the s orbital of the hydrogen axially or head-on, like this they are overlapping. So, this is known as axial overlap or head-on overlap. So, likewise methane is formed. C4 hydrogen CH4 is known as methane and the bond angle I said earlier it is 109 degrees 28 minutes. Then the bond length, if you take another molecule that is ethane, here only one carbon is there, here 2 carbons are there. In this is also has undergone sp3 hybridization where 4 sp3 orbitals are formed in a tetrahedral form and 3 of them are axially overlapping with the hydrogen s orbitals and one sp3 orbital is overlapping with another carbon of the same type. So, again this carbon has 3 hydrogens. So, here one bond is sp3 overlap of 2 carbons and the other 6 are sp3 s overlaps. So, therefore, CH bonds are 6 and one is CC bond and this CC bond length in sp3 hybridization is 1.54 angstroms. So, this is known as, this molecule is known as ethane where the molecular formula is C2H6. So, first molecule under sp3 is methane and the second molecule is ethane. The bond energy of CH bond energy is 99 and bond energy of CC bond is 83 kilocals. So, these are the ones and as I said earlier shape is tetrahedral. So, these are the characteristics of sp3 hybridization. Now, we will look into sp2, we will take up sp2 where I explained earlier that 1s and 2 p's are combining forming 3 identical energied new orbitals and those orbitals I have earlier shown you that they are all the 3 sp2 orbitals are directed towards the corners of the equilateral triangle and the molecule is seen like this. This is unhybridized p orbital. So, such type of two carbons will be combining forming a molecule. A single carbon cannot form like sp3. Here you cannot have a molecule with single carbon. You have to have two carbons here because of the presence of the unhybridized p orbital. So, two such carbons, they come closer and form a molecule known as ethylene, where the molecular formula is CH2 double bond CH2, that is known as ethylene molecule. So, this is sp2 hybridized, this is sp2 hybridized, both are coming together, where two of the sp2 are overlapping with the s orbital of the hydrogens axially, and this carbon also is using two of its sp2 hybridized orbitals overlapping with the s orbital of the hydrogen. Therefore, CH2 and CH2. So, this one another sp2 is overlapping with the carbon sp2. So, one sigma bond is sp2 overlap and the remaining 4 bonds are sp2 yes, sp2 yes, sp2 yes, sp2 yes overlaps. So, 4 are sp2 yes overlap sigma bonds and one is sp2 overlap sigma bond. So, total 5 sigma bonds are present in this ethylene molecule. The unhybridized p orbitals present on each carbon, they are left like this. They cannot overlap axially, they cannot overlap like this. It is not possible, you cannot bend this and then overlap. Therefore, they ought to overlap laterally, like this they have to overlap laterally. That is, this is the way they overlap. They come closer and then laterally above and below the carbon plane they will be overlapping, above and below the carbon plane. So, forming a pi bond. These are axial overlaps and forming sigma bonds. This is lateral overlap forming pi bond. Therefore, a pi bond cannot exist individually. It has to be along with the sigma bond. Once the sigma bond is formed, then only a pi bond can be formed. Therefore, in one double bond, one sigma bond will be there, one pi bond will be there. So, that is about the sp2 hybridization, and the bond angle here is 120 degrees. Wherever you see between two orbitals, it is 120 degrees and the bond length, CC bond length is 1.34 angstroms. So, this is about the sp2 hybridization and the example is ethylene molecule, CH2 double bond CH2 molecule. Now, coming to the sp hybridization, we will come to the sp hybridization. In sp hybridization, as already explained in part 1, 1s and 1p are combining forming two new orbitals. They are oriented linearly, collinear. The two sp orbitals are collinear. So, this is the collinearity, this side and this side. The bond angle will be 180 degrees always. It is a straight line. Therefore, bond angle formed between two sp orbitals is 180 degrees in sp hybridization. So, when one s and p are engaged, two are remaining, that is py and pz are not participating in hybridization and these are left like that. So, this is pz, this is py. So, two unhybridized orbitals are present. So, this cannot exist like this. Therefore, like ethylene, it has to combine with another such a type of carbon and form the molecule. So, this is the molecule you can see now. This is known as acetylene. Acetylene molecular formula is CH triple bond CH. So, here sp hybridized carbon is combining with another sp hybridized carbon and forming acetylene molecule. This is sp S overlap, sp S overlap, that is CH. Two CH bonds are present here. These are sigma bonds and two unhybridized orbitals, that is py. Laterally they overlap. This is the way laterally this pz overlaps, and laterally pz also overlaps. Py, pz laterally overlap, forming two pi bonds. So, therefore, similar to ethylene, here also these pi bonds cannot exist individually or independently. They have to be present along with the sigma bond. Therefore, in a triple bond, one will always be a sigma bond and the other two will be pi bonds. In a double bond, as I said, one will be sigma bond and the other will be the pi bond. In acetylene or in triple bond, one will be sigma bond and two others will be pi bond. So, now the bond angle I said in sp hybridization is 180 degrees and the bond energy between these two carbons is 200 kilocalories, and the bond length of this bond CC bond is 1.20 angstroms. So, these and the shape I said already, it is a coplanar in collinear. Shape is collinear, angle 180 degrees and bond length is 1.20 and bond energy is 200 kilocals. This is about the sp hybridization. So, in sp3 we have discussed methane is the example. In sp2 ethylene is the example. In sp hybridization acetylene is the example. So, now we will pass on to the general characteristics of carbon compounds. What are these general characteristics? As I said earlier, carbon compounds, they form covalent bonds. Because they form covalent bonds, they have low melting and boiling points because intermolecular forces are weak here. So, easily the molecules can get separated. Therefore, boiling melting points are very low in these carbon compounds. Then, these are not highly polar. Therefore, these compounds are soluble in non-polar compounds such as legroin or petroleum ether, benzene, carbon tetrachloride, etc. They are not soluble in water. Only polar compounds get soluble in water. As you all know, the common phrase that is like dissolves in like. Non-polar dissolves in non-polar, polar dissolves in polar. Therefore, the carbon compounds which are non-polar dissolves only in non-polar compounds. Then, these compounds cannot conduct electricity either in a solution or in a molten state because they are not ionic. Therefore, they cannot conduct electricity. More than that, they can burn readily. So, these are the general characteristics of these carbon compounds. Now, we will pass on to the topic how to name these compounds. Naming these compounds, so many numerous compounds are there, how to identify them. In order to identify these compounds, we have to learn to name these compounds, and this system is known as IUPAC system. IUPAC is the abbreviation of International Union for Pure and Applied Chemistry. So, frequently used and mostly used is IUPAC system, and rarely chemical abstract system is used. Now, there is no need to get into the details of the chemical abstract because mostly used is IUPAC system. Now, we will look into this system of naming the organic compounds. In short, I have shown here as a flow sheet. Here the IUPAC name consists of 3 parts. The main part is the middle one, that is the root word, and the next is suffix, and before that root word comes the prefix. So, middle will be the root word and the prefix will be comprises of the names of the substituents. What does this prefix mean? Substituents details. So, details of the substituents, what are hanging onto the ring, those are the names which are referred as the prefix. Then what is the suffix? After the root word, suffix comes at the end, where the functional group name, saturation, unsaturation, and then the functional group name comes. So, therefore, the flow sheet contains these 3 parts, that is the root word, suffix, and then prefix. Prefix, as I said, it is given as the position of the substituents and the position of the subchains. Then coming to suffix, again suffix is of 2 types. One is primary suffix and then secondary suffix. What is this primary suffix? Primary suffix indicates single bonds are there or double bonds are there or single bonds. It clearly shows or explains the way the chemical bonds are there, whether single or double or triple bonds. Then coming to secondary suffix, other than these functional groups, what all we have discussed in the part 1, alcoholic, aldehydic, such type of a flow sheet was there, all those functional groups can be named as a secondary suffix. So, now we will take up few examples, rules, we will discuss about the rules and then one by one, and we will end up with the examples. Now, coming to root word. Root word indicates how many number of carbons are present in the longest carbon chain. First, what you should do is, in a chemical compound, longest continuous carbon chain has to be identified. Again I am repeating, longest continuous carbon chain has to be identified, and how many number of carbons are there must be counted and the root word must be fixed there. So, if 1 carbon is there, it is named as root word must be meth, and 2 carbons it is eth, if 3 prop, 4 it is said as but, and then 5 pent, likewise 6 hex, 7 hept, 8 oct, 9 non, and then 10 dec. So, these are the root words you have to use depending upon the number of carbons present in the longest continuous carbon chain. After fixing the number and the root word, then what you should do? You should number the chain. Should number the chain as 1, 2, 3, 4, 5, 6, 7 in such a way that the substituents or the functional groups gets the least numbering. The substituents must get least number. In such a way, the chain has to be numbered, whether it is a functional group or the subchain. They must be numbered. For example, if you have such a chain, here if you see 4 carbons, completely 5 carbons are there, but they are not continuous. What I said? Longest continuous carbon chain. So, this is the longest continuous carbon chain. This is not, this is out of the chain. Again, this can be a continuous carbon chain, but 3 carbons are there here. Here, this is the longest carbon chain where 4 carbons are there. Which is the longest chain now? So, this has to be selected. 1, 2, 3, 4. They should be numbered as 1, 2, 3, 4. Either this side, from this side also you can number as 1, 2, 3, 4. But this is considered as the substituent and this must get minimum numbering. From this side If you count, it is getting 2. From this side if you count, it is getting 3 as the number. Therefore, the number which is the minimum for the substituent has to be selected. Therefore, the numbering starts from this side 1, 2, 3, 4. So, that is the rule for fixing the root word. So, now we will pass on to the other. So, on the other hand, the functional group contains carbon atom, then it should be numbered as the number 1. This is nothing but when a carbon is present in the chain, continuous carbon chain. For example, this is the example it is given here. So, here CHO is known as aldehydic functional group. This is in continuation with the carbon chain. Therefore, this functional group must be numbered as 1. Invariably, the functional group, if it contains carbon, it has to be numbered as 1. So, in this molecule, you please look here, in this molecule, the functional group gets 1 and the other ones progresses like this 1, 2, 3, 4. So, when 2 are there, this is one functional group, this is another functional group. Which one has to be given a least number? Now, another rule is there, that is known as the priority rule. According to this priority rule, you have to give least numbering to these compounds. Now, this is the priority rule. These are the compounds where priority must be fixed. The first one COOH, second COR. So, just go through these priority rules, you must remember these compounds. When COOH and CHO are there, the first preference must be given to COOH group and the second preference to aldehyde group. In case if a COOH group and OH group are there, COOH must be given first preference and the next preference must be given to the aldehyde group. Now, coming to the suffix, the primary suffix indicates saturated or unsaturated, already I said. If it is a saturated one, the primary suffix must be used as ane. When the single bond is there, the primary suffix must be used as ane, and when a double bond is there, the primary suffix used must be ene. And if it is a triple bond in the carbon chain, then the primary suffix must be used as yne, Y-N-E. Then coming to the secondary suffix, along with the double bond, any other functional group is present, then it will be termed as the secondary suffix. So, what are these secondary suffixes? For example, ol, alcohol, this must be said as a secondary suffix. Then you should use OL. If it is an aldehyde group, AL must be used. How you should be used? The terminal E of the primary suffix must be replaced by the secondary suffix. If it is ene, E must be replaced with OL, ene, ol, enol, it becomes enol. So, likewise, if it is AL, ene, AL, E is replaced with EAL, enal, enal, AL, enol, enal. So, in that way it must be enone. So, E must be replaced with these secondary suffixes. In that way, it has to be named. So, these are a few examples of the functional groups, how they are named in the named as a secondary suffix. They are given in the table. Almost all the functional groups are given in this table. So, at the end, I want to conclude as saying, the first thing what you are doing is, you are fixing the root word. Then, depending upon the number of carbons, then you are identifying the prefixes and then putting them before the carbon chain in the English alphabetical order. If more than one substituents are there, then they should be placed in the English alphabetical order. Then comes the suffix. Suffix must be added to the root word, and again in the suffix primary and then secondary I said. So, these are the things which has to be remembered before naming. If the same substituents repeats more than once, then you can use di, tri, tetra. So that's how you can name the compounds, and let us see few examples now. So this is the example. One example I will be discussing. Here 5 carbons are there, as I discussed earlier, the minimum number. So therefore this is 2-methyl. This is the prefix. 2-methyl is prefix. Pent is the root word. Ane is the primary suffix. And here it is C5 chain, and here 2-chloro and 2-methyl. Alphabetical order, C comes first and M comes next. Therefore prefixes. These two are prefixes to the root word. Then pent is the root word, ane is the primary suffix. So likewise you can have another example here. Here if you take this, the 5 carbons are there, therefore pent is the root word and the ane is the primary suffix and al is the secondary suffix. So pentanal. And another one, if you get into this, 2 are there. So here pent is the root word, ene is the primary suffix, al is the secondary suffix. Hope I am clear in this IUPAC system. Now you go through the different books and then refer, take out the examples and then write down the names of the compounds so that you can become perfect. So many books are there, Ferguson and then Crack and Hendrickson, Organic Chemistry by Crack and Hendrickson, and Morrison and Boyd, and Google also, you can Google it and then see. Blue book is there, red book is there for IUPAC nomenclatures. Please go through these systems and books and you can learn more about this IUPAC system of naming the organic compounds.